we are taking up a very, very important topic in climatology, or for that matter, any studies for climate or related to the weather patterns on the earth. This is topic of insolation and how is it related to the concept of net radiation. Talk about winds, talk about the global patterns of temperature or rainfall. The fundamental to all atmospheric processes is the energy that the earth receives from the sun. So the incoming solar radiation is what is called as insolation. And insolation on an average is around 1340 watt per meter square. Or we also have a number in terms of another unit, which is about 2 calories per cm square per minute, also called as 2 Langleys per minute. The energy that comes into the planet, this energy is measured at some height of the atmosphere. As a convention, the height at which they measure all of this is at around 800 to 1000 kilometers, which is more or less the boundaries of the atmosphere. Okay? This figure is approximating to that height above the Earth's surface. Now, many people confuse between the concept of insolation, which is the incoming radiation, and the concept of net radiation. Now, when I use the word net radiation, I am not just referring to what the Earth receives, but also referring to what the Earth is losing. This net radiation includes the net long wave losses. They include the net losses from the Earth's surface and also from the atmosphere. So when I talk about the receipt and the loss and then try to balance off what is the pattern, I call that as net radiation pattern of the Earth, okay, of and from the Earth, whereas the insolation refers to what the Earth receives. So in geography, we have a concept called as heat budget. The concept of heat budget includes the idea of net radiation. Of course, net radiation does include the idea called insolation, but they are not the same things. Now, in insolation, we have to know a couple of things about the pattern and the factors that are responsible for the receipt of the energy at the atmospheric boundaries and the receipt also at the Earth's surface. So if I imagine this as the Earth surface and this as the boundary of the atmosphere, this is the insolation at the outer levels of the atmosphere, and after some losses, after some absorption, this is what I receive at the Earth's surface. So the insolation receipt at the atmosphere is not same as the insolation receipt at the surface, and there are latitudinal patterns on this. What are the factors that decide the amount of insolation the Earth receives on surface? We have factors related to scattering, diffusion. There's some absorption of radiations here. We also have reflection. There are losses because of dust particles in the atmosphere. So by the time we receive the insolation on the surface, it is far less than what we have in the outer atmosphere. And this varies. The variation can be as much as almost 50% of variation, 40% variation, and even more sometimes. And again, the difference also depends on the length of the day, the type of surface we have. So if I have longer days, I will have more insolation, and probably in areas where the atmosphere is less thick, the insolations coming in will be much more higher. So there are many factors. I'm not elaborating all of them. Why? Because I assume you know these factors, and I'll take you through the textbook when I'm discussing in detail. So I hope you understand. Okay, the insolation pattern is related to what comes in, and I'm comparing the insolation at the outer atmosphere with the insolation on the surface. Now the pattern tells us that there is a gap, and the gap can be pretty a significant gap, implying there's a lot of losses that happens in the atmosphere. The difference is maximum for the poles. In fact, if I look at the maximum radiation that the Earth receives at the outer atmosphere, the maximum insolation is for the poles. And if I talk about what is the maximum losses, the maximum losses is also for the high latitudes. This is because the distance traveled by insolation in the atmosphere in the high latitudes is more than the distance traveled by the insolation in the low latitudes. I think we all know this. It's because the earth is a curvature, and the distance in low latitudes is almost straight displacement distances, whereas I move towards high latitudes, the distances that the insolation must traverse is much more in terms of length. Why? Because the rays are slanting. So I think you all know this. Now I would like you to look up some discussions in the textbook. Again, I refer to Savindra Singh, climatology. We have followed extensively the Savindra Singh geomorphology, and now I recommend that you all must have Savindra Singh climatology. Of course, this is for those who are giving geography as an optional subject. Others, you need not worry about this. The page numbers are again more or less the same. So I'm referring to page number 37. In fact, the section starts from page number 34. This is page number 34, chapter number 3. The topic is insolation. Now in page 34, second column, we have this last section, maybe the last 8-9 lines. It says, it is obvious that solar constant refers to the rate of radiation from the sun, which is of the value of 2 grams calories per square centimeter per minute. It is also expressed in terms of Langley. Each Langley is calories per square centimeter. Essentially, this figure is called as the solar constant. It's an average that we have what the earth receives at the outer layers of the atmosphere. Now, you can look up page number 37, distribution of insolation. Page 37, distribution of insolation. Now, the pattern of insolation is very well depicted on page number 38. Page 38, there is a graphical representation. Now, please look at the graph, and on the graphs, I have already named them E for equator, although they're already labeled, but to help you, I've mentioned E for equator. The dotted line is the insolation received at the outer layers of atmosphere, and the solid line is the insolation received on the Earth's surface. The gap between them, the dotted E and the solid E, the gap between that is the losses that the insolation has to go through because of the atmospheric thickness. Similarly, we have the HH graph, the insolation for the high latitudes, and we have the TT graph, the insolation pattern for the tropical and subtropical latitudes. Now, what we can see very clearly is that the highest amount of insolation received in the outer atmosphere is for the high latitude, which is the high latitude dotted line, which has a very sharp peak, which means that at any given year, the maximum insolation for a month is received at the North Pole or at the poles. And that's because the poles are towards the sun for a longer time. But look at the solid line of H. It says latitude 80 degree north. The solid line is far more smaller than the dotted line for the high latitudes, which means the losses in the high latitudes are very, very high. Whereas compare the lines of E, the dotted line equator and the solid line equator. It's almost fairly uniform, as in the energy received by the earth at the equator is almost same, with a peak at equinox when the sun is directly overhead at the equator. It's a slightly more at equinox, whereas for all other latitudes, the maximum is at solstice, which is the time when the sun is overhead at the tropics. So for equator, we have this pattern. Now, if you compare this discussion with what is written in the textbook, so please, you can follow me on the textbook now. Page 38, first sentence, it says, it is apparent from the table 3.2 that the amount of solar radiation reaching the outer limit of our atmosphere is significantly more at different latitudes than the amount of insolation received at the ground surface. This trend reveals the fact that a sizable portion of incoming solar radiation is lost while passing through the atmosphere due to cloudiness, atmospheric turbidity, reflection, absorption, and so on. The data of insolation as portrayed is in the table. It says further, the table further reveals that the maximum insolation reaching the outer limit of the atmosphere at the North Pole at time of summer solstice, while the maximum insolation is received at the ground surface between latitude 30 and 40 degrees north. Now see, let me explain this to you. Compare the three solid lines, the solid line E, the solid line T, and the solid line H. What you find is the highest value for the solid line is for the subtropical, tropical latitudes, which is maximum in June 21st, which means if we look at the insolation received at the outer atmosphere is maximum at the poles, but having accounted for the losses, the maximum insolation received at the surface is for the subtropics. And that is because the subtropics have high pressure conditions, the subtropics have sinking air, less cloudiness, we have deserts there, so we do not have much of a cover for more reflection or more losses in the atmosphere. That is why the subtropical latitudes receive the maximum insolation at the Earth's surface. We move on to the next page, page 39. The first line, it says, the table reveals the fact that the total amount of insolation received at the Earth's surface decreases from equator toward the poles. Okay, and look at the last three lines of this paragraph. Okay, and I insist on this. When I'm teaching you through the videos, we do not want you to simply listen to the videos. We want you to pause, rewind if required, sit down with a pen and paper and keep jotting as I teach. And whenever I open up a page, I would like you to open up your textbook, underline and make a jottings as I teach. Simply listening to the video as a presentation or a short movie will not help you at all. Any case, you must go back and rewind again. But before that, you can be with me. So let's get on again. Page number 39, the first column, first paragraph, the last three lines. That the globe is divided into three zones on the basis of amount of insolation received during the course of a year. Low latitude zone, mid latitude zone, and the polar zone. So I have explained what is the pattern of insolation at different levels of the atmosphere and at the Earth's surface, and we have compared this insolation for different latitudes. And we also mentioned what are the reasons why we have differences in the insolation received at the outer atmosphere and what are the losses by the time the insolation reaches the Earth's surface. So page number 41 is that list of what are the reasons why the insolation varies on surface and at the outer atmosphere. So length of day, distance of between Earth and Sun, the sunspots. Page number 42 talks about effect of atmosphere. And I'll suggest the effect of atmosphere discussion is more important. I repeat, what are the reasons why the insolations received on the Earth's surface can vary across month, can vary across days, can vary across years. The variations are because of length of day, because of the distance of Earth atmosphere from the Sun, because of the sunspot cycle. Sometimes the sun gets hotter, at other times the sun gets cooler. But the more important reason why we have variations across latitudes is because the properties of the atmosphere. The atmosphere can absorb, the atmosphere can reflect, the atmosphere can scatter, and that creates so many variations in the insolation patterns. So that is what we have in page 42 and 43. Okay, effect of atmosphere includes reflection, albedo component. It includes diffusion, okay, and absorption and scattering. Scattering is one type of diffusion, and the scattering depends on, again, the ratio between the size of the particles in the atmosphere, dust particles and so on, with the wavelength. So if the ratio is more, we have some type of scattering. If the ratio is less, we have another type of scattering. When the ratio is more, the size of particles is larger than the wavelength, we call it as Mie scattering, M-I-E. Otherwise, it's called as Rayleigh scattering. Page 43, second column. Okay, look at the first paragraph, scattering. And this is mentioned in about 7th or 8th line. It says, in general, the process of scattering becomes effective when the diameters of the dust particle and the gas molecules are smaller than the wavelength of the solar radiation. Okay, and this is called as Rayleigh scattering. The next paragraph, it says, the second law of scattering was by Mie. It says that when the molecules have a larger ratio of diameter wavelength than those that give rise to Rayleigh scattering. So we call this as Mie scattering, M-I-E. If your answer has some of these mentioned, your answer looks nice. Okay. So I've discussed something around insolation. What is insolation? The variations of insolation on the outer atmosphere and the surface. How this pattern varies at different latitudes. What are the factors why we have the variations? The next is the concept of net radiation. Now, in net radiation, I don't talk about insolation alone. Now I talk about the insolation and the outgoing radiation together. And we try to even off the losses and find out what is left as net radiation. So net radiation is a part of discussion of the heat budget. Okay, and you must know both the concepts to talk about what is the temperature pattern and what controls the temperature, okay, zonation across the Earth's surface. Now, to understand the concept of net radiation and some discussions there, we can look up page number 49 and 50. So a very short write-up here. So it says, page 49, net radiation and the latitudinal balance. It says, the difference between all incoming solar radiation and all outgoing terrestrial energy by both short wave and long wave is called as net radiation. So what comes in is insolation, what goes out are the losses. If you take a net of that, we get net radiation. It is apparent that the aforesaid discussion that the net radiation for the whole globe is at least theoretically zero, but this is far from truth. So if I look at the Earth atmosphere system in long-term perspective, we say it is at balance. If it was not in balance, the Earth would have been becoming progressively hotter with every moment. The Earth would have been progressively cooler with every moment. But this is not the case. There's a good, very nice balance between what comes in and what goes out. This is mathematically. But if we look at more shorter frames in real time, there are variations. Okay, there are variations. Look at the next page. Next page, first column. Okay, the two paragraphs. Okay, you can leave the first 5-6 lines or 10 lines approximately, where it says this mechanism. I repeat, page 50, first column. Look at the 5th line from top. It says this mechanism results in the development of areas of energy surplus, okay, and areas of energy deficit. Energy surplus, where the insolation is more than the out losses of radiation, and net deficit is where the losses are more than the insolation. In the next two paragraphs, it has discussed two type of patterns. The pattern of net radiation at the level of the outer atmosphere and the pattern of net radiation on the Earth's surface. These are not the same things. So I repeat, the first one, okay, the first one, it says the energy surplus and the energy deficit areas may be identified and studied at two levels. Number one, at the Earth's surface, and number two, in the atmosphere. So I'm looking at, by the time the energy reaches the Earth's surface, something else has happened here. So we look at net radiation at both the circumstances. What happens to net radiation in the atmosphere and what happens on surface. The first discussion is the distribution of net radiation at the Earth's surface from the equator towards the poles shows that there is a large energy surplus between 20 degree north and 20 degrees south. The tropical areas for the surface, the tropical areas around 20 to 30 have the maximum amount of net gain. B, look at the sixth line from here, it says, net radiation rapidly decreases from energy surplus areas to low latitudes, towards the mid latitudes. Net radiation practically becomes zero at 70 degree. If I'm comparing the net radiation on the surface, it becomes almost zero at 70 degree latitudes, whereas the polar areas are zones of perennial energy deficit. Now compare this with the insolation pattern. I said insolation, the maximum receipt is at the North Pole. But if you look at the net radiation on the surface, the maximum receipt is between 20 degree north and 20 degree south. The next paragraph is the latitudinal distribution of net radiation in the atmosphere. So I've discussed the surface. Now I'm discussing the net radiation in the atmosphere. The patterns are a bit different here. It says that on average, the atmosphere is itself a net loser of radiation at all latitudes. If I compare the atmosphere with the surface, the atmosphere is net loser. Okay, the losses from atmosphere are more than what the atmosphere gains at any given time. Thus, the atmosphere is a zone of perennial energy deficit because the deficit of energy always exceeds 60 kilo-Langlis and so on. And then there are 2-3 points. It says, if the data of net radiation of both the Earth's surface and the atmosphere are combined, the net radiation for the combined Earth-atmosphere system may be so calculated. And the pattern is that large region of surplus extends between 40 degree north and 30 degree south. So now this is a point of comparison. If I talk about the net radiation for surface alone, then the energy surplus is between 20 degrees north and 20 degrees south. But if I look at the combined effect, then the net surplus is between 40 degrees north and 30 degrees south. And similarly, the northern latitudes are deficit and the southern are and the southern latitudes again deficit as I move towards the high latitudes. So this was a quick discussion that we had, and of course a very nice discussion. Same page, last lines, page 50, first column, the last lines. It says, it means that there must exist a two-way heat transfer. Now, once I've established that at any given time, the tropical areas are areas of surplus and the polar regions are areas of deficit, then there has to be some mechanism that tries to even off this difference. Now, this mechanism operates two ways. One is, there's a mechanism by which there is vertical transfer of energy, so that the atmosphere and the surface tend towards equalization, plus there will also be some kind of transfer across latitudes. Energy must go from the areas of low latitudes towards high and then back. So I repeat the sentence, page number 50, first column, last lines. It says, it means that there must exist a two-way heat transfer from the Earth's surface to the atmosphere and from the equator towards the poles. This can be achieved if the heat is transported from the Earth's surface to atmosphere and from tropical and subtropical areas to the surplus of surplus radiation to the high latitudes of the deficit radiation. So if this is the Earth's surface, this is the tropical regions, and this is the atmospheric height, then there are two types of heat transfer. One is transfer from the surface toward the atmosphere. Why? Because the atmosphere at any given time is net deficit compared to surface. There has to be some kind of vertical transfer at every latitude. Plus, There's some transfer from low latitudes towards high latitudes. So we have got vertical management of energy deficit, and we also have the latitudinal management of energy radiation or insolation deficit. So I hope you have got the concepts. You need to review this discussion. So watch the video 2 or 3 times, make notes, and I hope you understand what we have been discussing in this. Thank you.